Hello.
Also sharing the screen.
Can you hear me and see me?
Great. Yeah.
Okay.
Yeah. Then, so it's yours.
Thanks. Thanks to everyone for joining this meeting. I will jump on the same train and say that I'm a physicist trying to understand the brain. So I will start with a very basic statement, which is, which is the brain is a complex system with dynamics on very different time and spatial scales. So regarding the spatial scales, we can, for example, look at a single neuron, which can have a degree of freedom D. We can look at the interaction of neurons to put it together in a neuronal population. And we can also look at power, especially on the right side of this. And in many cases, it is not necessary to know what the individual neuron is doing. It is sufficient to know how the population response, for example, is to external stimuli. So what we can use are so-called neural mass models. And I will present one such neural mass model, which was developed a few years ago. And we made an extension of this model to include short-term synaptic plasticity. But first of all, I will start with the original model. So we start with a population of quadratic integrate and fire neurons, or in short, QIF. So these QIF neurons are described by a differential equation, which looks like this. We have a membrane time constant tau m, and we have this quadratic membrane voltage term on the right-hand side. Without this reset rule, this differential equation, it would just explode. So as soon as the membrane voltage VI reaches some threshold, we reset it to minus V. We want these neurons to be connected, and we do this in an all-to-all manner. So we have a coupling weight J, and every neuron sees the firing of every other neurons. So in this way, the synaptic connections are realized via this term, which is proportional to the mean firing rate R, which you can see defined here. So we can add another term, which is just simply some constant current to tune the system. So we have these network equations on the left side. So we have for each neuron, we have one equation describing the membrane voltage dynamics. So we have n equations. And for this type of network, an exact mean field limit was developed. So in the limit to infinitely sized networks, we have an exact neural mass model. Instead of describing the individual neuron, we will describe the system in terms of the mean firing rate, this R, and the mean membrane voltage, this V. This neural mass model, this original Montbriot model, has been studied already quite extensively. And it has a bifurcation structure which looks something like this. So we have as a bifurcation parameter this current eta. For small current, we have a stable node. For large currents, we have a stable focus. And in between, we have some multi-stable regime with these twofold bifurcations. If we want this neural mass model to interact with other objects, for example, some external influence or other populations, we can force the system. We can add some external forcing. So in the original model, for example, if we start the system here and we add some sinusoidal forcing, we just, in the first part, we just remain on this stable branch of equilibria. At some point, if we go further to the right, there's no other option other than to approach the stable focus. So we go up. Since it's a focus, we will get oscillations. So we will approach the focus more and more using having these fast oscillations and follow the stable focus branch, and at some point jump down again to the stable node, such that we generate this bursting limit cycle. Now we took this model and extended it to include presynaptic depression and facilitation. So presynaptic depression and facilitation refers to the fact that the synaptic strength between neurons is not constant in time. And these time-dependent quantities U and D represent two different phenomena. The first one is depression. Depression means if a neuron fires, the synaptic weight towards other neurons becomes weaker. So as an illustration, we have the firing rate of a population here. Firing rate increases. This depression coefficient decreases. And facilitation is basically the opposite effect, which means it is a strengthening of the synapses. So here the firing rate increases and this U coefficient increases. And these two effects take place on two different timescales. So this is 200 milliseconds and this is 1.5 seconds. We now take these presynaptic depression and facilitation dynamics and plug it into, on the left side, into the network equation. So the firing rate, the recurrent connections are now multiplied by this U and D. And also in the neural mass, we do the same. And we get these two additional equations in both systems. So we have in the network n+2 equations, in the neural mass 4 equations. And to have some more interactions, we can add a time-dependent external current. This neural mass limit is exact. I will show you a quick example. In the first panel, you see a simulation of the network using many, many neurons, and each dot represents one spike of a neuron. Here you see some external current, which I feed into the system, and as we feed the current into the system, the neurons start to fire synchronized. And here on this panel, you see the firing rate of the neural mass. And you see that it's perfectly coinciding with the firing of the network. So here you see the exact limit, and we can use such models to answer questions which are related to working memory. You see this reference here, which is a preprint. And yeah, this is just one application, which I will not get into the detail. I want to talk a bit more about the possible external currents which we can feed into the system. So basically this I1 of t. This I1 of t could be due to some interaction with other neuronal populations. It could be due to some cortical oscillations like delta, theta, beta, and gamma waves. Or it could be simply just external stimuli like visual or acoustic stimuli. And I want to keep it general here and simple also. So I will choose a sinusoidal as the external forcing term. We have some amplitude A, and we have some frequency epsilon, which I choose to be small. Small in the sense that it's small compared to 1 over the membrane time constant. I will show you a little preview of what dynamical behaviors we can get in such a system which is externally forced. So these are, for example, subthreshold oscillations. These are also subthreshold oscillations. And if we increase the amplitude, we can get bursting. We can get more bursting. We can also get something which looks like bursting, but which is not a complete bursting cycle. We can get something which is called Canard. So the firing rate increases and suddenly we have a fast jump here. We can get a Canard with a head. We will see it later. So we have 2 jumps here. And I will try to explain these different dynamical regimes and in a slow, fast analysis framework. So to do so, the first thing we need to do is to make the differential equation autonomous. Right now, we have explicit time dependence here in the sinusoidal term. So to remove it, we let the sinus be generated by 2 additional differential equations, these 2. And we add these 2 into our system. So now we have 4 equations, these 4 in the top for the neural mass, and 2 orange equations, which are only there to generate the sinusoidal forcing. This whole thing is in parameterized in the time variable t. But we can also use as a parameterization the slow time, which is the small parameter epsilon multiplied by t. And if we do so, the whole differential equation system is transformed. So in the fast time variable, the epsilon multiplies the right-hand side of the forcing variables. And in the slow time, we can find it on the left-hand side. So since this forcing is slow, we can take it to the limit and take the limit epsilon to 0. And what this means, in the fast time, we will obtain the fast subsystem here. In the fast subsystem, I1 and I2, the derivatives are 0. So the forcing is infinitely slow. So I1 is just a simple parameter. In the slow subsystem, the limit to 0 gives us the 4 differential equations of the neural mass to be not differential equations anymore, but these green equations. These are simply algebraic equations. And these 4 green equations have a special meaning. They define the so-called critical manifold of our slow-fast system. As a general remark, the fast subsystem and this epsilon to 0 limit, the fast subsystem approximates fast dynamics and the slow subsystem approximates slow dynamics. And the meaning of this critical manifold is also different for the 2 systems. So in the fast subsystem, the critical manifold defines the equilibrium. So we have here the bifurcation diagram. The I1 is now a constant, so we can use it this sum as a bifurcation parameter. We see, similar to the original Monte-Briot model, we have some equilibria at small currents. We have equilibrium on the right side, which is stable. In between, we have 2 folds and unstable equilibria. At the same time, there's a Hopf bifurcation, a subcritical Hopf bifurcation, generating this family of limit cycles, this purple curve. Okay. In the slow subsystem, the critical manifold defines a state space. So slow dynamics take place on this critical manifold, which has the same shape as the bifurcation diagram. And I denoted with this darker shading that these equilibria on the critical manifold correspond to stable equilibria of the fast subsystem, and the fainted color is are unstable equilibria of the fast subsystem. We can now take this framework to talk about the different solutions which I have just shown. So we can start with a simple case of subthreshold oscillations. If we look at this curve on the bifurcation diagram, we see that we simply remain on this equilibrium, on this bottom equilibrium branch of the bifurcation diagram. In terms of the critical manifold, we see in the I1, I2, the forcing variables coordinates and the R variable. So these cycles are basically generated by the 2 differential equations of the forcing. So just the sinusoidal term and the other one's the cosine. And as we move along the circle, we move along the slow dynamics, which are described by the state space given in the slow subsystem with the critical manifold. So we follow, we follow the shape of the critical manifold. So the firing rate increases and decreases following this surface. Okay, now for this trajectory, which I call Canard, they increase, then we have a jump, and then they start to follow the slow dynamics again. This is a quite well-known phenomena in slow-fast systems, so I will not get into too much details. But what we see, what makes this trajectory special is that we, in the full system, we follow the equilibria of the fast subsystem. And we continue to follow this, although these equilibria are repelling now, but the full system remains on this object. And at this point, we jump down again. So a typical, these are called canard because if we rotate it, we see some canard, which is a duck. These canards are quite well known. A typical example is the Van der Pol oscillator with 2 equations. So we can have these canard segments following a little part of this repelling sheet, or a maximal canard following the whole part of the repelling sheet, or we can have a canard with a head, which jump up onto these attracting equilibrium. If we want more details, we can do it in the end. For our system, the canards look as we expect on the critical manifold. So we follow the critical manifold until this upper sheet and jump down again. So these canards basically exist due to the existence of an object which is called a folded saddle equilibrium. It creates a connection between the attracting part of the critical manifold to the repelling part of the critical manifold, allowing this trajectory to remain on the critical manifold until this upper fold. Okay, now we come to these canard-like trajectories. These canard-like trajectories look like the canard with the head of the Van der Pol oscillator. But I don't call it canard because the main difference to the van der Waals oscillator is that these upper equilibria, they are repelling. So they are not stable, they're unstable. But still, the full system, the fully forced system, lifts off this equilibrium and lands on this repelling stuff up here. And then since the forcing goes back, we go back and jump down here again and have two fast jumps here and here. So on the critical manifold, we are on the slow dynamics. We remain on the critical manifold on the attracting sheet. We have the folded saddle, which helps us to remain on the critical manifold, although it is repelling here. We lift off, which is still fine. And then we land on the repelling part, which is counterintuitive. So this critical manifold is shown in I1, I2, and R coordinates, but we can also plot it in different coordinates in I1, V, and R. So we have one forcing, one slow variable and two fast variables here now. This green trace is still the critical manifold, and the blue curve is still the same Canard-like cycle. And if we look at it from the front, so in RV, it looks like it is all the dynamics takes place on this surface, on some kind of surface. And the surface turns out to be defined by an equation, namely by this one. And this somehow suggests that there's a third timescale which you have overlooked. Because if we look at the differential equation for the firing rate, and if we put something like an epsilon here and take the limit epsilon to 0, we will obtain the equation which defines this surface. It is not a very rigorous way to argue about these third timescale, but for now it's sufficient. So there seems to be an additional timescale in the fast subsystem, and this additional timescale gives us a different critical manifold. And the counterpart to this critical manifold is a slow subsystem made of 3 equations now. So we ignore the 2 very slow variables, I1 and I2, but have these 3 slow variables now. This system made of 3 equations has an equilibrium, which has the same equilibria as this green curve, but it's not 3-dimensional. And the black dot, the landing point here, it is still unstable. So even in this reduced system, we have an unstable equilibrium up here. But the key point here is that it has 2 unstable directions and 1 stable direction. And via this unstable direction, it has an associated 1D stable manifold, which is shown here. And it turns out that this 1D stable manifold connects the middle sheet of the critical manifold to the upper sheet of the critical manifold, although it is unstable. But there is a connection which allows to lift off this middle part and land on this top part. So yeah, it explains these Canard-like trajectories by considering a third timescale, which was not obvious. Okay, so this is a Canard again. Now we come to the emergence of bursting. I changed a little bit the parameters. The half-wave equation was located here before. Now it is located on the middle sheet. I did it to prevent unwanted interactions with a delayed hop, but it's not so important now. So if we look at the subthreshold again, we just remain on the lower branch of equilibrium, and if we increase the amplitude, we get some little Canard segment here, and on the way back, when the forcing is going back, as we pass by this fold, the second fold, we get oscillations. So here it is again together with the critical manifold. We follow the critical manifold, we get the Canard segment, and then we jump and get oscillations and go back to the critical manifold again. And it is a bit surprising that we have these oscillations, because in the fast subsystem in this region, there are no foci. There are no periodic solutions, because the only periodic solutions, the limit cycles, are these this purple bit. So what causes these fast oscillations? And to answer this question, it's a bit tricky. We have to consider equilibria which are in the system, which are a bit unphysical because they are at negative firing rates. A population cannot have negative firing rates, of course, but in the neural mass, these equilibria exist. And we will neglect the external forcing for now. So we will say the current is constant. It's not changing anymore in time. And if we take this constant current, for example, denoted by this black line, we have two equilibria. The first one is this top one, shown here in R, V, and D coordinates, and the other one is the bottom one. The bottom one is a saddle focus. It has one stable direction and two unstable directions. And it turns out that these two unstable directions form a 2D unstable manifold, which contains the upper equilibrium. So in other words, we have connections from this rather unphysical equilibrium to the regular equilibrium. And these connections, they contain some sort of cycle oscillations, but these are not true limit cycles. We have a heteroclinic connection between these two equilibrium. And we have such a connection for each external current value. So this is again this bifurcation structure and the bursting trajectory. And for a fixed current, we have one of these heteroclinic connections. So this is this negative R equilibrium. This is the regular equilibrium, and it is connected via this cycle, via this heteroclinic connection. So for the bursting trajectory, we start here. We follow this black line, the bottom equilibrium. We go up this short canal segment, and near this upper fold, the full subsystem interacts with these heteroclinic orbits such that it follows this trajectory, and we get these oscillations for each slice of these external currents. And in the end, we get this kind of trajectory. And this trajectory was obtained for a relatively large epsilon. If we decrease this epsilon, so if we really go towards the singular limit, these oscillations will more and more go into the form of the limit cycle, of the true limit cycle of the fast subsystem. So it means these heteroclinic orbits are somehow a ghost of these true limit cycles. And as we decrease epsilon, we will go into the shape of these limit cycles. But even in absence of this limit cycle, we have these fast oscillations due to the existence of these heteroclinic orbits in the fast subsystem. So yeah, it was a bit surprising that the bursting is emerging due to these heteroclinic orbits. I will just simply shortly summarize the main results. So there's a hidden timescale separation in the neural mass model with short time plasticity. We have seen the existence of these Canard-like trajectories, which is also surprising since they land on an object which is repelling, but they can be understood taking into account this third timescale. And we have seen the emerging of the bursting via these heteroclinic orbits, which are present in the fast subsystem. As an outlook and future work, we would like to have a more rigorous approach to this hidden timescale, because there must be some transformation where we can really see the epsilon of this third timescale. And these Canard-like objects, we know the main results I have shown here were obtained using the neural mass, but we know that the neural mass is corresponding to some network and that it's an exact limit. So if we are accurate enough, we should find also all these solutions in the corresponding network. It will be just much harder. And also regarding the network and these heteroclinic orbits, we have seen that there's an equilibrium at negative firing rates, but for the neural mass. And the network, we cannot expect to have equilibria at negative firing rates. So the question is, what is the role and the interpretation of these equilibria for the network? And can we find this kind of orbits? So yeah, that's it. That's basically it. Thanks for your attention.
Yeah, great talk, Halgurd. Thank you very much. Very instructive. There's another question by Emre Bashbina. Thanks for the talk. It's very nice. I have two questions. One, where does the equation describing the surface, like the critical surface, which you showed on slide 18, come from? And then the second question, on the same slide, you mentioned that there appears to be an additional timescale. Maybe you mentioned it and I missed it, but what is its relation to the other two timescales? Is it the slowest one or the fastest one, or timescale between the other two?
Okay, so you're talking about this surface equation, I suppose, Emre. It was a guess, basically. This equation, I mean, the right-hand side is obviously the right-hand side of the R equation. So we assume that there seemed to be a third timescale by putting some epsilon hat in front of this R. But it's as I said, it's not a very rigorous way to make this consideration, and we would like to do it properly. This is feature work, but I can tell you the relation. So in this case, R is basically the fastest variable. Then we have V, D, and U as some intermediately fast variables or slow, and I1 and I2 are the slowest. Yeah.
Great. Yeah, I think that answers the question. Yeah, in the interest of time, we have to move to the next speaker, but
sorry, it was a bit long.
Yeah, maybe, well, we can maybe do this one. There's another question by Marius Yamaku. Thanks for the interesting talk. Can we prevent your Canard solutions by introducing some randomness, which is very relevant in neurodynamics?
He is probably speaking about these Canard solutions, or Canard solutions in general. I guess so, yes. If we introduce, okay, so this type of Canard-like solution was due to this stable manifold of these upper equilibria. And I think in the perturbed system where epsilon is not zero, so in the simulations, I believe that this is quite a narrow stable manifold. So if we introduce noise, probably we will not hit the stable manifold and not be able to land on this and probably start bursting. I don't know. It's something, noise is something which we have not considered yet.
Okay, great. Yeah, thanks a lot, Halgurd.
My pleasure.